Right, so we're going to the section on distributed training, and this requires us running things on a virtual machine, multiple GPUs, and also we cannot run the stuff on a notebook. So we're going to do some setup, have some credits for run pod. So what I'm going to do is um, choose, let's say this one. I'm going to choose 4 GPUs. We need at least 4 for this exercise. On demand sounds good. Maybe I think I'll increase, uh, yeah, the volume to say 60. Yeah, let me check how much memory is expected. Disk space to allocate of at least 40 GB. Okay, this should be good. So let's deploy. Um, so basically, we are going to create a virtual environment, install the dependencies, and then yeah, and then um, just copy the minimum stuff that we need for the setup, like the imports and stuff, and yeah, and try to solve the exercises from there. Okay, let's see. Can I connect to my terminal? And yeah. Alright, we're in to do is move into the workspace. There's nothing here. I'm going to create a virtual environment here. Let's quickly look up. Uh, mhm. Right, so I just need to do this. Let's call it Arena, I guess. And then okay, we're in. So now we're going to install stuff. Go all the way up to here. Yeah, I need I need to do this. What else do I need? I need Jupyter and IPython. Uh, I'm planning to not use Jupyter, um, but I'll just install it anyway. And yeah, I'm going to run this anyway. I'll need stuff like Torch, NumPy, Torch Fusion. Let's do that. PyTorch, pip Linux. I don't know which CUDA version I'm using. How do I find out? Hmm. Oh, seems it's 12.1, and yeah, let's do this. It's pretty quick. Yeah, so we need to do, then we need to install numpy on p torch vision. Now we get torch vision. I think we also get numpy with this. Yeah. Okay, let's just install 1p. I'm not sure if we get TQDM by default. Let's install that. I think we have everything else. Oh, we have everything. We already have 1p. Okay, cool. Now what we're going to do is um, can I have my VS Code connect to this via SSH? Let's see. Let's open VS Code. Um, let's need the SSH command. Let's take it from here. Hmm. Could not establish connection. Why is that? Let's see. Mhm. Okay, let's go back. Let's close the connection. Let's look at the docs for import. Mhm. Mhm. I guess I need to copy this and then I think we're connected. Uh, hmm. Let's see if we can get a terminal here. Hmm. I don't make a separate directory. I think it's fine. Now I just need to create files here. I'm going to create a file to set up everything. How do I? Hmm. Mm, yeah. And now in this file, I'm going to have my have to have this code. I need to do this. Or do we have to be in a notebook for this? Mm, okay, so let's do something else instead. Let's connect to Jupyter Lab and we'll move this into here. And yeah, and we'll just run this here one time. Let's create a notebook. Oh, let's creating a new launcher. Here, let's just do this. Do this. Hmm. Hmm. Uh, my bad. I need to change this to root, and the branch would be what? Master file. Hmm. I'm going to extract this. branch is master file, then chapter is this. Yeah. Oh, unzip not found. Okay, skip. Hmm. Why can't I just clone? And then alright, so we will do this and this, and where do we want to do this? I can just do it here. Um, yeah, I think if this works, hmm, okay. Uh, source pin arena pin and now I run this. Hmm, 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 hmm. My bad, my bad. Oh, I guess it works if it's a path in the string. Hmm. No problem. Let's do it manually. Hmm. Bear with me, guys. It's going to be worth it. And we get this running and solve those exercises. Let's see if this works now. Hmm. If I need a skill learn for something, wait, what happened? Okay. Rich. Hmm. Okay, what does this mean? Actually, we don't need this, I guess. Or do we? Do we need it somewhere? Hmm. Can't tell if it failed. Yeah, it's definitely some exception. Current working directory. Go through the parents. See if this chapter exists. In which case, we are going to go here. Sizes, session. Enough. Mm, okay, so think we're closer to making it work. Uh, what else do we need? What else do we need? Think mostly okay. Let's see. Okay, I'm just going to start reading now. Uh, yeah, and figure out issues as they come. Distributed training involves spreading workload across multiple workers. Improves the speed of training. It's most beneficial for large models, compute demanding tasks like deep learning. Main families, the data parallelism and model parallelism. In data parallelism, we split patches of data across different processes, run forward and backward separately, accumulate the gradients, update the model parameters. Model is segmented into different parts that can run concurrently in different nodes. horizontal and vertical, depending on whether you're splitting the model up into sequential or parallel parts. Horizontal parallelism is called tensor parallelism because it involves splitting up the weights in a single layer across multiple GPUs. What we commonly call sharded weights. And vertical parallelism is called pipeline parallelism. They're both widely used and can be more or less appropriate in different circumstances. It's possible to have hybrid forms, especially common when training large models like the frontier LLMs. We'll just focus on data parallelism for now, although we'll suggest a few bonus exercises that explore model parallelism. Interesting. Okay, so the exercise below will take you through data parallelism. Start by learning how to use the basic send and receive functions in PyTorch. Mhm. We got the GPUs. You'll use those two primitive point-to-point functions to build up some more advanced functions. What are the primitive point-to-point functions? Okay, I guess we'll see them below. We're going to implement broadcast, gets a tensor from one process to all other processes, gathers all tensors from different devices to a single device. All reduce combines both broadcast and gather. Are key parts of how distributed computing works. And then finally use these functions to build a distributed training loop. Mm, so yeah, my idea is to do everything in a Python file. So the code below is a simplified example. Distributed communication between multiple processes. For the unique rank for each worker, we create a new Python interpreter called the child process. Execute the function passed to it. Function has to have the type signature of this. Hmm. Total number of processes is determined by well size. This isn't the same as the number of GPUs. We require the environment variable set before launching. The former specifies the IP address or host name of the machine coordinator. Since we're using a single node, all we need to do is get an unused port on the machine. Hmm. So init process group initializes each process with a common address and port, and the communication backend also gives each process unique rank so they know who's sending and receiving. Okay, have we imported this somewhere? Yeah, okay. Mm, I want to go through this code by typing it out. Mhm. Yeah, the function is being run by rank 0. Think can copy this rank and well size. Then we create a tensor of zeros and send it using this dot send, and if it's run by rank 1, hmm, we're doing some simple communication. In this case, we want to send a tensor of all zeros, and we send it. We want to print rank. We want to say we want sending this tensor. Excuse me. And then if we have rank 1, we want to mention created answers of all ones. We print it, then we receive. And then yeah, we overwrite the received answer, the data we get from rank 0, and we print it. Finally, we do this destroy process group. Uh, okay, it's called at the end of the function to destroy process group and release resources. Basic primitives for point-to-point communication between processes. Hmm. Okay, there are primitives for collective communication also. Each receive for a given process, source process, will wait until it receives. This is a send from that source to continue, and likewise each send to a given destination process, we'll wait until it receives further process. These are blocking operations. Okay, let's run this. Um, we do so by just running. Oops, what happened? Connection reset. Hmm. Uh, to move here by doing. Huh, forgot to activate the virtual environment. Oops. Hmm. Here we go. Okay, so we'll now adapt this to work with multiple GPUs. Yeah, I think we do have multiple GPUs. Let's just check for Torch SD. Yeah. Let's first read into the backend document. The three main backends for distributed training: CPI, there's Glue, and WCL. First two are general purpose, support both CPU, GPU, and server communication, while NCCL is GPU only protocol. Hmm. Oh my god. Okay. So when sending and receiving tensors between GPUs, CCL backend, send and receive tensors should be of the same type. Tensors need to be moved to the GPU before sending or receiving. No two processes should be using the same GPU. So because of this, especially the third point, each process rank will be using GPU with index rank. So this applies to data parallelism and NCCL backend paradigm. So in general, this is not necessarily true. So we're going to change the code a bit. Uh, we're going to have 100 for NCCL. I need to get my device. Yeah, similar to this. Tensors need to be moved to the GPU before sending or receiving. I think they mean GPU here because you're not creating a tensor on GPU. Yeah, makes sense. So what we do is give a device and yeah, I think everything else will stay the same. Yeah, let's run this. This is strange. Is it stuck? What's happening? Uh, get the device based on the rank. Hmm. Yeah. Yep. All right. Okay, we are going to look at collective communication, operations that synchronize data across multiple processes rather than just two. Three important kinds. This broadcast, where we send one tensor from one process to all other processes, is gather. We collect tensors from all processes, concatenate into a single tensor, and as reduce. Instead of concatenation, we do some reduction, just like gather. Hmm. So the latter two functions have different variants depending on whether you want the file visit to be in just a single destination processor or in all of them. This gather is all gather functions we're most interested in building are broadcast and all reduce. The former for making sure all processes have the same initial model parameters, and the latter for aggregating gradients across all processes. Okay. Implement broadcast. So we're going to do this, then broadcast averaged gradients from rank 0. Okay, so we already have the tensor. So we have two cases. If rank is 0, we do something else. Uh, we do something else. So if rank is 0, we need to be sending our data. Uh, so do something like uh, yeah. Um, so we print this. Uh, we do this. We need this. This dot send answer answer destination. Can I give multiple destinations? Probably not. So and if you're not the source rank, then you just do you create a receive tensor. It's to be of same type. Uh, hmm, uh, wait a minute. We already have tensor, so just do this. Uh, think this should work. Let's see. I already have that. Hmm. Wait, what happened? Come on, again. Hmm. Trying to initialize the default process group twice. Hmm. Because I forgot this. I guess I have to see how we're being tested. Let's go to tests. Mm. Oh, it's already doing this for me. So all I need to do is hmm, where's going broadcast? Right, so I just need to do. I don't need to do any of this. F equals 0, send it, let's receive it, and alright, looks good. Uh, yeah, I think we tried it with 3 GPUs. Pretty good. Let's look at the solution. If rank equals source. Did I? Yeah, I think I have it correct to 0. Um, Okay, now let's do all reduce. Yeah, let's do all reduce, and I think yeah, we'll be doing this in the next session. For now, we'll just do all reduce. So reduce, to do reduce and all reduce. So if the rank is not the destination, we need to do something else. We need to do something else. So if the rank is destination, we need to receive other rank, as they call it. What we're going to do is tensor. We're going to do something like this, and then we're going to receive and source ping the receive other rank, and then finally we copy. No, we don't copy. Do we have INOPS? No, but we can do. Right, so we do copy saved answer plus. Hmm, a bit unsure to do this. Hmm. This is the average so far. Let's say we have, yeah, let me just show it here. Let's say we did average of three tensors. So we have some sum of three tensors by three, and we now also have some uh, new element from new tensor that we received. So what we can do is so we can just do this. We don't have this, we have one size. So what we do is one size plus new tensor dot one size. So all we need to do is this plus so divided by one size. Hmm. And if rank is not destination, what we need to do is send the gradient to destination, and we can do that by simply doing this. Yeah, let's also print. Let's test reduce. Oh man, why is it timing out so often? Uh, hmm. That's good, I guess. Hmm. I like to see how this was tested. We have initial tensors. Hmm. Okay. Now we have to do all reduce. So across all ranks using 0 as the initial gathering rank. I wonder if we can't just call reduce for each possible destination starting from 0. Hmm. This is much more efficient. Yeah, yeah, this is definitely much better than just um, calling reduce on each one. So if you can reduce once, um, okay, I also like this. You just keep adding the received tensors, and only if it's main, just divide it by one size. Because this will only happen after all of this to receiving from every possible destination. I like that. I think I'll do that. And then if it's a main operation, then also divide um, by one size. Uh, Reduce and then broadcast. Broadcast is tensor. Uh, Hmm. Hmm. Okay, what's next? A simple model, and it's basically talks about how to train a simple model using this parallelism across GPUs. Okay, uh, I think I'll pause now. What I'm going to do is, yeah, I don't need this. Yeah, I'm going to stop and continue next time, where I'll do, I guess, this exercise. Yeah, I think we'll go through this. I'm not sure if I'll implement them. Um, yeah, I don't want to spend more than a couple of hours on this anymore. So that would be it. Yeah, so yeah, see you next time. Thank you.